Today we have the tutorial 2. Once again, this session is being recorded and we'll be able to see it on ULearn soon. Today we'll do some examples on Laplace transforms, and before we go into Laplace transform examples, we need to make sure that we understand this table. So basically this table is going to show. So f of t and f of s, we will have the f of t and f of s as the Laplace transform pairs, in which ft is in time domain and f of s is in frequency domain. And if we see here, these are the basic transform pairs. So if this u of t is 1 upon s, e to the minus at is 1 upon s plus a, t is 1 upon s square, and so on. Just to make sure that we are defining all these functions for t greater than or equal to 0. Okay, and whatever we have before t equal to 0 will be 0 in time domain. So sometimes we'll see there will be a function u of t attached to the function. So sometimes we'll see that f of t is written with u of t. This shows that this function is valid after t equal to 0, right? So don't get surprised if we see u of t attached with the function. That is actually highlighting this thing, right? And then we have the properties of the Laplace transform. So you can see that it applies linearity, scaling, time shift. You can see that here it is showing ut minus a, so it is showing that it is after t equal to a, and so on. If it is differentiated in time domain of certain order, what we will see, we saw some questions for differential equation yesterday as well. So all this time integration, initial value theorem, final value theorem, these are the properties that we will be using. So in today's session, I am going to show you how we can use these tables to find the Laplace transform. We are not doing the integration of Laplace, which is not required, especially for this course. Maybe if you're taking a course in maths or something, then you can go for that. You can still use it, but it will take a lot of time to solve those integrations. All right. So let me take you to tutorial 2. Okay. So today we'll see some examples, and we'll make use of those tables to find the Laplace of this. All right. So what do we see here? We see that there is a u of t, which I just mentioned, that this u of t is showing that f of t is f of t is equal to 0 for t less than 0. Okay, so don't get surprised with this u of t. The main function is basically cos 2t and e to the minus 4t. So if we look at the tables here, we have these functions available, like cos omega t is available here, and e to the minus something t is also available there. So we'll make use of this, but these are not exactly there as it is. So we have to see how we can make use of the tables. So for cos omega t is s upon s squared plus omega squared. So cos 2t, cos omega t is s upon s squared plus omega squared, right? And for e to the minus at is 1 upon s plus a. E to the minus at is 1 upon s plus a, right? So I think it's very obvious, very easy to relate that here this is omega and this is a. This means if you are trying to find the Laplace of this function, cos omega t will be s upon s square plus 4, because it's 2, omega is 2, and plus 1 upon s plus, what is it, 4. So 4. This is the Laplace of this function. I hope you guys are okay. Now, if we want to simplify it, we can simplify it by simplifying it and get this as the answer. As long as you are not taking a wrong property, as long as you're not taking any wrong Laplace transform, if you leave it like this is also acceptable. If you simplify it, then it's even better. Right? Can I proceed? This is probably the simplest one. Right? T square cos 3t. T square cos 3t. Now, once again, we know that the basic function is cos omega t, which relates to s upon s square plus omega square. But what do we have is a t square multiplied with it. So we have to go and check which property is it that we can use that will help us. So this is f of t and this is f of s. And there is a t square with f of t. What happens to f of s? We'll go back to the tables. Okay, do we see somewhere there's a t somewhere there? Anyone? Which property to use if we want to like find the Laplace for the given function? Can anyone unmute their mic and tell me which property to use?
Frequency differentiation.
Somehow I can't hear. Can you say again?
Frequency differentiation.
Why can't I hear from this one? Okay, so I have to disconnect. Just give me a second. So we're talking about frequency differentiation, TFT, minus d upon ds of f of s. But do we have t over there or t squared in the function? So let me just put this one as it is. It is the one given is t f of t is related in Laplace transform is minus d upon ds of f of s. Do we have it like this? We have a t squared. So probably not mentioned here, but we can break this. Like this is one function and we find fit just for t only. And then we multiply again with t with the previous one and we get. So basically this will be differentiated again with this negative sign again. So basically it's like t to the power n f of t relates with minus 1 to the power n d and its derivative of f of s. Right? And I think this we did it in while we were doing the Laplace transform pairs. So 2.2 is it? 1. This is inverse Laplace. It should be 2.3.1 actually. No. Yes, this one. And yeah, this one. You can see this one. If it's t to the power n, it will be converted into Laplace transform by having a -1 to the power n and nth derivative of f of s. So if you come back to our function, this is the one. So let me take out the ink from here right now. So f of t is equal to t square cos 3t in this one, ut. And the one that we know is cos omega t will be s square plus omega square. But now we have to use t to the power n. F of t will be -1 to the power n dn of s upon ds n. So nth derivative. So second derivative. So if I want to find f of s of this function, will be equal -1 to the power 2, okay, and second derivative of s square plus 9. All right. Anyone not clear about this? Anyone wants to get a second opinion on this? Please raise your hand if someone has a problem that I can explain. Okay. And let me proceed to the. So now you just have to differentiate it. I hope you know this is u upon v, vu dash minus uv dash upon u square. Just let me just put it here. V u dash minus u v dash upon v square. We differentiate it twice, so we have to do it twice, and then eventually we get this as the answer. All right, I think you can continue from here. All right, can I proceed to the next one?
Yes.
Thank you. Okay, find the Laplace transform of the gate function. So, given a mathematical expression, and then you have to find Laplace. But now we don't have a mathematical expression, but we have a signal in terms of x and y axis, a function shown graphically. Again, not a big problem. First thing is to get a mathematical expression for the graphical representation. Okay. Can anyone, would someone want to tell me how to find the mathematical function of this graphical representation? Anyone? It's like something from your signaling systems. Is my sound muted? Can you hear me?
Yes, sir.
Oh, I thought my sound was somebody said okay. So, can someone give me a hint, maybe a hint how to find this function in mathematical representation? Anyone? It's very easy, by the way. Okay, GT is 10 to okay. Jocelyn has got something for me. It's okay. Very good, Jocelyn. The one with two. Okay, this is also okay. Foundation is also okay, but we need a mathematical expression. So yes. All right. So basically, it's like this. Suppose we have this as the time axis, and suppose this is not there. So can I say that there is something, a step function like this? So if it is starting at 2, wouldn't this function be u of t minus 2? A unit step function delayed with 2 sampling instants, right? And it is disturbed by, like it is like blocked here. So after this time, this thing is gone. So something is subtracting from this particular signal, which would be another step function that starts at t equal to 3, which is u of t minus 3. So if we add them, or as actually subtract them, not add them, subtract them, um, okay, if we subtract them, we'll get this particular function. Agreed? So you can see it will be this and this and this with an amplitude of 2. So basically, this function, let me call it g, like she's also said g as well, is equal to 10, amplitude is 10, I'm sorry, 10 u of t minus 2 minus u of t minus 3. Agreed? Do you guys understand? So this is the simplest function. We can use the same approach because ut is just 1. If we take a look at u of t, this is 1 at t equal to 0 or at a particular time. We can use this one for the existence or the non-existence of any function. We'll see in a few examples next. Okay. Okay. All right. So now we have to go and check which function relates to this. Let me go to my Laplace transform pairs. Do we have any u of t here? How did this come? I want to have this as my picture. Okay. Go back. Okay. So ut is very simply 1 upon s. Okay. So for our function, where we have ut but delayed. So ut is related with 1 upon s, but now we have a time delay of 2 seconds and 3 seconds. We go back to the tables again. Let's the properties of Laplace transform. Okay, which one shows a time delay? No, this is the which one shows a time delay? Which function, which property shows a time delay? All these properties, you can name them, linearity, scaling, and all. It's very obvious, by the way. But which of the property shows a time delay? Anyone? Time shift. Yes, I'm Tian. Thank you very much. So you can see that this property is delayed by a seconds, a sampling instance. So we go back, and what happens is that whenever it's delayed, the same delay appears in e to the minus as. So if it is u of t minus a, it will be e to the minus as 1 upon s. So in our case, it will be 10 e to the minus 2 upon s minus e to the minus 3 s upon s. All right. And we can again simplify it. I don't want these anymore. Can simplify as 10 e to the minus 2s upon s 1 minus e to the minus s. This is just to simplify, but you can leave it as it is, no problem. All right, I hope this makes sense to you guys. 10 upon s, e to the minus 2s, e minus to the minus 3s. That's the answer. But this is very important because now this can be used as, this example can be used as any function which is between any particular time, between t equal to 2 and 3 or whatever time it is, we can use this property. All right, example 4, very similar. So I believe some of you can easily, you can do with me as well. So we can say this h of t is equal to, for this part, it's 20 between 0 and 4. So 20 u of t minus u of t minus 4. Is that okay? Does that make sense? And of course, it's not ending here, plus 10 u of t minus 4 minus u of t minus 8. So we use the same property as we did in the previous example to express this particular function. I think the rest is just history for you guys now. It's 20 f of s is 20 e to the minus 20 it will be 21 upon s minus e to the minus 4 upon s plus 10 e to the minus 4s upon s minus e to the minus 8s upon and then you can simplify. All right, anyone, any question? Anyone, any question? All right. Okay. So if you simplify, you will get this. All right.
Sir,
Yes, go ahead.
sir, can you go back to the first example again, sir?
Can you hear me?
Yes, I can hear you, sir. Can you go back to the first example?
Third example.
First example, sir.
First example. This one?
Yes, sir.
Right.
So you converted the cos 2t and the e negative 40 into a Laplace transform, sir. So you should do the same for the ut as well, sir.
UT is actually just showing that this function is valid from t equal to 0 onwards.
Oh, okay.
Nothing else. If there is just u of t, then we look at
Okay, sir.
that it is starting at t equal to 0.
Okay, okay.
Right?
All right, sir. All right, sir.
Is it okay?
Yeah, okay, sir.
Sometimes because Parinda, is it okay?
Yeah, okay, sir. No problem.
Your speakers aren't working. Switch to a different device. Why are my speakers not? Can you hear me?
Yes, I can hear you. Can hear you.
Can you guys hear me?
Yes, yes.
It looks like okay. I hope you can hear me. Let me hear on this side. Can you hear me? I think it's okay. Okay, I hope you can hear me. If you don't get my voice, please let me know. Your speaker is muted. Is it okay now? Okay, thank you.
Yes, sir. Yes, sir.
All right. Looks like my headset is not working. All right. So I move to example 5. Okay. Don't show me the answer. Okay. What we see here is that we have a periodic function, and once again, luckily, some guys helped us to devise properties for periodic function as well, time periodicity. So if there's a function f of t, if you can see this, if a function f of t is periodic with a particular period n and t, so the Laplace of that function will be, you just take the first period and divide it by 1 minus e to the minus s, where t is the period. So just let's say a function is periodic with a period 4, for example. And suppose the Laplace transform of that function is, let's say, 10, just 10. So it will be 10 divided by 1 minus e to the minus s 4. Okay, so I'm talking about that if we have, I cannot, if we have a function, suppose whatever it is, if f of s is suppose 10 and the period is 4, so whatever that function was there, we just take the first period and we take it 10 divided by 1 minus e to the minus 4s. It is as simple as that. So what we need to go through is to find the Laplace of this first period only, actually not this first, we have to take where it is repeated. So what is the period of this function? Can anyone tell me? What is the, first of all, is it periodic? How do we know that it is periodic? It is repeated after a particular say interval of time. Can someone tell me what is the period of this function? Is it 2 or 5? 2. Sharif, is it 2? So 2 or 5? Let's get a poll. Likes for 5 and likes for 2. Okay. Yes, it's 5. Basically, it is repeated after this time, not just this. Okay. So we can say that t equal 5. So we just need to find out the you need to find out the Laplace of this function for a period of 5, then we can simply use the property. So let's find out what is the function for this one. So we can see is there a name ft. Is there a name? It looks like. Or if I can. So f of t, let's call it f1 because it's the first period. We can see that it started with ut, but it ended at minus ut minus 2. And for maybe clarity, we can say that this is between 0 and 5, t, small t. We don't need to write because it's like obvious from the figure, but still just to make sure. So if we first find the Laplace for f1t, so f1 of s is equal to u of t is 1 upon s. Now we should have it on our fingertips now, minus e to the minus 2s because this is time delayed upon s. So 1 upon s times e to the minus 2s is the Laplace, or we can say that it's 1 upon s 1 minus e to the minus 2s, right? So what's next? We go back to the table. We need to divide by 1 minus e to the minus this thing. Where is it? So we go back here. So t is there. Remember that f1s divided by 1 minus e to the minus ts. Will it be cancelled? Interesting. So f of s is equal to 1 upon s 1 minus 2s divided by 1 minus e to the minus 5s. Right? Is that clear? So it's very easy if we have the have a periodic function. We just find the Laplace of the first period only, and then we proceed with dividing with 1 minus e to the minus st. Any question? Okay. So we move to example 6. This is the answer. So this time we have another periodic function. So maybe those who are graphically good in graphical representation, it's much easier, but those who might need some help, let me just show you this one. Once again, it's periodic with a time period of 2, and of course it's between 0 and 1, so we are expecting something like ut minus 1. This is something that we expect because it's only non-zero between the first period. How do we write this function? It's basically we find the slope of this line, which in this case is very obviously did not find a slope. We need to find the equation of this line, actually, equation of the line. So there were so many methods, if you remember, 2-point method or slope point method or something. But let me just take, suppose we are given any function. In this one, it's like this one. I'm using the 2-point method. So this point is 0, 0, and this point is 1, 2. So 0, 0, 2, 1, 2. The equation of the line is y minus y1 upon y2 minus y1 equal x minus x1 x2 minus x1. If I'm confusing you with this and you know a better method, you can go with that. But I have used this one, which has never failed me. But if you have like any other method, you can for sure do that. So y is basically f of t. Is it f of t? Yeah, f of t minus y1 is 0. Divide by y2 minus y2 is 2 minus 0 equal x is t minus x1 is 0 and t2 is 1 minus 0. So it's basically ft is equal to qt. Okay, you can use any method. This is what I like, but if you have another method, and once again, I'm not teaching equations or graphical representation, but once again, whatever method you like, you can use that method, right? So the function is basically 2t. We multiply this here, 2t ut minus 1. This is f of t. So we find f1 of t. So we find f1 of s. So what is the Laplace for t? If you remember, you go back to the tables. The Laplace of t is 1 upon s squared. Okay, so we can bring it from there. So 2t is 1 upon s squared minus, if it's t minus 1, will be e to the minus s upon s squared. Or f1s is 1 upon s squared 1 minus e to the minus s. Please take a look at it. Let me know if you have something that you don't understand. Anyone is okay? Do I have Lukman here? Lukman is not here. Okay. All right. Anyone, any problem, any question? All right. Yeah, this is what we get at the end. Obtain the initial and final values of this g of s. Once again, if you go back to the properties, we have the initial value and final value theorems. F of 0 is limit s tends to infinity s f of s, and f of 0, the final value, is limit s tends to 0 s f of s. Both of them are multiplied with s, but initial value has s tends to infinity and final value has s tends to 0. And just to remember that time and frequency are reciprocals. So if t is 0, frequency is infinity. If t is infinity, s is 0, right? So I come back to this. Initial value is very easy. Initial value is f of 0 equal limit s tends to infinity s f of s, which will be limit s tends to infinity s times 6 s cubed plus 2s plus 5 divided by s s plus 2 square, s plus 3, s goes with this s, and if we apply the limit, okay, so remember we cannot apply the limit if it goes infinity upon infinity. So either we make it look like something else, or we, so just for that sake I am taking s cube common from the numerator. It will be 6 plus 2 upon s square plus 5 upon s cube, divided by this will be s square plus 4s plus 4. I'm taking s and we multiply, then we take s cube common, will be s s square plus 4s plus 4 and s plus 3, and in the denominator will be s cube plus 3s square plus 4s square plus 12s plus 4s plus 12, and in the numerator is 6 plus 2 upon s square plus 5 upon s cube. Can I come here? And taking s cube from the denominator as well. S cube, it's 1 plus, it's 3 plus 4 is 7s square. So 7 upon s plus 12 plus 4 is 16. 16 upon s and plus 12 upon, to be s square, 12 upon s cube, right? S cube goes with s cube, and now if I apply the limit, since now it's infinity, this will be 0 and this will be 0, this will be 0, this will be 0, and this will be 0. We get limit, we get the function initial value f of 0 equal 6. Very dirty work. I'll give you a 0 if you do it like this in the exam. Okay? Don't do it like this in the exam. This is the luxury of being a teacher. All right. For final value theorem, you cannot apply like that. You have to make sure that all the poles of the function are on the left half plane. I did not mention this before. This is the S plane. And if you remember from signal system, this is the region in which the system converges, or the system is stable. We don't have to use stability concept in here, but anyways, the poles have to lie on the left half plane. So all the poles should be either negative or with negative real part. So as long as, so we have to check, or maybe 0 as well, or 0. So there is one pole at 0, one at -3. We have to find the poles for this one. So it's also at -2 and -2, right? So the poles are at 0 and one at -2, another at -2, and one at -3. 0 and -3. So that satisfies the condition. Okay, for initial value, no problem. We just apply limit s tends to infinity, s times f of s. Okay. For f of infinity, we can apply s tends to 0, s f of s if all poles are on left half plane or the axis. So no pole at right hand plane. So our function was, I believe, s. What happened? Our function was, come on, with the denominator. What's happening? Oh, I'm clicking on the s plus 2 square and s plus 3, or we can say it was s plus 2, s plus 2 and s plus 3. This shows that the poles are origin -2 and -3. So it's okay, it's all on the left side. We can continue finding it. So multiply with s, put the limit, and we can find the final value here. Final value. Is it okay? I think you can find the value. All right, example 8 is the convolution of two signals, which for me at least, it was sort of nightmares always. Okay, if there's any question, I can take it now. All right, just to give you the flavor or some shivers, I would say, from your signal and systems. How would you do it? You take one of these functions, you flip it, then you make it so that it's just like sliding, and you keep on sliding as it starts to intersect or overlap the second function. You keep on doing that. You check the limits. So what happened to the like starting point, ending point, and so on. To give you the idea, something like this. So in this case, x1 is considered as the one we flip and then we shift. So it's, you can see this x1 of minus lambda, just flipping, and then to make it shiftable, x1 t minus lambda. Just for those who are getting scared already, don't worry, this is not what we are covering in our code. This is just to introduce you with how convolution makes things easy. All right, then we start sliding. So we have to start sliding this function with this function, and we see that, okay, when does it start to overlap, when it's completely overlapping, when is it uh, starting to leave the function, and when it has already left it. So you see we started to slide it at t equal to 1. You can see at t equal to 1 it will start to overlap, and this will continue until something next happens. So it starts to overlap, and after t equal to 2, so once this edge has passed this point, this has also passed this point because the width is 1. So we have to take care of all these things, and we keep on multiplying. So we actually see that after t equal to 2, it is completely overlapping, and it will continue to do that until t equal to 3, because once t equal to 3, this function is leaving it. You can see that this has left this function. And this phase will continue until t equal to 4, when it has completely left. Right? This is like this. And for each of these limits, so we can see that this is the case when t is less than 1. There is no multiplication, no overlapping, so output is 0. When we come across here, we see that after t equal to 1 and before t equal to 2, we have multiplication. Can I show you? Yeah. So after between 0 and 1, between 1 and 2, between 2 and 3, between 3 and 4, and after 4, each one will have a different value depending upon. And looking at these functions, we can see that we not only have to multiply but add as well. So as we keep on, so let's say if this is starting to overlap, so multiplication is 1 into 2. But as you move forward, we'll have more values overlapping. That's why we have more values and so on. That happens until 2. And so initially the output is increasing. Then when it's completely overlapping, so the output will remain constant. And when it has left or starting to leave, it will decay or go down, and then after that will be 0. So the function would look like this. This and this. This is what we used to do, and this is a very simple two very simple pulses multiplying or being convolved. What is convolution, by the way? Anyone, any idea what is convolution? Have you done convolution other than this? I open the question. I open the floor for answering. Have you ever done convolution in your life other than these graphical ones? Anyone? Okay, let me tell you, you have done it. You have done it. You have done it many times. It's the same process actually. What do you think, guys? Anyone? Can you hear me first of all? Multiplication. Okay. What multiplication? We did multiplication here as well. We are multiplying these two functions. We are multiplying these two functions. But is it just multiplication? What multiplication, Azreen? So one domain to other. No, we have done it. You have done it. You have done it many times. Let me skip. You have done it. Every one of you have done it, and let me just tell you when. Let's say it's x squared plus 4x plus 4, and another function is x plus 5. So yes, multiplication. Multiplying two polynomials is actually convolution. What do? We sort of flip it, not necessarily, but and then we start to multiply. So we multiply this into this, we get x cubed, then we move it forward. You want to, somebody wants to control? Sing? Okay, I allow you. You want to say something?
No, sir, I'm just mistake.
Okay, I was so excited.
Sorry.
No problem. So to maybe you can press escape. How to end the control? Stop control maybe.
I don't know.
Okay. So let me come back. So basically, we are sliding and multiplying and adding. So x squared plus so x squared times x is x cube. Then we multiply with plus 5x squared. Then we move forward. Now this is already moved forward. Then we move further forward. 4x comes here. 4x squared. Then move forward. 4x times 5. And then 4 comes here is 4x and plus 20 and so on. So this is actually convolution, right? So this happens, basically this happens when an input is applied to a system to get an output. And why is this important? Because we will be applying any voltage source or a current source to a circuit and to find the output. So this is why convolution is important. It's like we have one input, we apply to a system and we get the output. That's called convolution. And if you want to do it in time domain, where's the time domain? This is time domain. And just imagine all these steps, but if it is to be done in frequency domain, you find x1 of s and x2 of s, you multiply them and you get the output. So I leave that to you and before we break out into the sessions. Any question? Have you guys seen the problem sheet? Let me just show you the problem sheet if I can find it. So I hope that you have already identified your group members now by now. So same rules, everything. Please save the file name with the problem name. Okay. Last time it was all very good except you did not save the file name with the problem name. Okay. Okay, we have again 15 questions, and once again 1, 2, 3 will be M1, M2, M3, and so on. They are all shuffled, so there is no complexity in that. But I want to keep the same M1, M2, M3 for the one that you used before. And you have to use the Laplace transform table and properties. No need to do them with hand, with integration. All right. Any question, guys? So once again, how you will be doing the tutorial session, the group work. You don't have to solve the question here. Some of them actually are like very easy, so you can do them. But eventually, you have to do them later on and submit before tomorrow. Tomorrow, maybe 5 p.m. You have to discuss among yourselves, show the table and the properties table, and see which property to apply. Maybe for the ones with graphical representation, maybe you can discuss how you would express them in time domain, like mathematically here, and then later on you can do the problem and solve them and upload the video or the. So before we leave, please go to once again the poll for. Where is it? Class timings. We just have 27 so far. I need all of them because we want to do it officially. Please, can we do it now? We have almost all the students here. Can we do it now, please? Before we break for. So I want all 32 names, please. We are 32, maybe 29 right now. Is Faraz here? $29. Okay, looks like okay. One more, please. 30. Okay. 28. Okay, they said, oh, who is this? Ah, thank you. Because we cannot do this if we have even one student not agreed. All right, Jocelyn will make one more time the poll for the conduct. I'm stopping the session here, the recording session here, so that later we will upload it and we will break that. Stop recording.